Hi everyone, this is Hongyu, and today I'm delighted to present our work, an empirical study of ROT for Linux, the success, dissatisfaction, and compromise. This research is a joint effort between Beijing University of Posts and Telecommunications and the University of Electronic Science and Technology of China. As the foundation of the digital world, Linux supports various applications in our daily lives, such as mobile apps, server-side software, and even autonomous driving systems. However, Linux has long been plagued by various bugs, as illustrated by the bottom left picture and oops error commonly seen during kernel debugging. Like Linux, other system software also suffers from numerous bugs. One interesting fact is that memory bugs accounted for around 60% of all bugs, a significant portion. The Linux community has made numerous efforts to address these issues, including static code analysis, dynamic runtime detection, and site testing. Despite these efforts, the number of bugs, especially memory bugs, hasn't significantly decreased. At this point, a new programming language, Rust, has emerged. Rust is known for its memory and thread safety due to its ownership mechanisms. Thus, one natural idea is to utilize Rust to develop the kernel. The Rust for Linux project began in response to the challenges proposed in 2019. It aimed to integrate Rust into the Linux kernel. After 3 years of iterations, it was finally adopted. Rust for Linux promotes to enhance safety without compromising performance. Thanks to its safety capabilities, Rust has earned acknowledgement from Linux. Before diving into Rust for Linux world, I will introduce some background about Rust. Rust's safety ability is ensured by two rules. First, in Rust, each memory address can only be owned by one variable. And second, the compiler ensures that all references to this memory address are valid and within the variable's lifecycle. This prevents memory bugs, but these strict rules can limit the language's expensive for complex data structures, particularly intricate data structures like double-linked lists. To address this, Rust introduced the concept of an unsafe block, allowing developers to bypass safety checks when necessary. This feature allows the architecture of Rust for Linux. The left part is the C code, and Rust for Linux uses Beijing to generate a corresponding Rust code within the same memory layout, and call the C function with FFI. The process of calling another language from Rust involves unsafe blocks because the other languages are not checked by the Rust compiler. The medium part is the kernel crate, which generates safe wrapping of unsafe code. The architecture ensures that unsafe operations are isolated and controlled, providing safe interfaces for driver developers. The isolation is crucial as it allows developers to build a secure foundation without constantly worrying about underlying unsafe code. It has already been proved effective in other systems. Well, we know about Rust. Rust for Linux is rarely studied. Therefore, our paper focuses on three main aspects. What's the current status of Rust for Linux? Does the Rust for Linux live up to the hype? What are the lessons learned from Rust for Linux? Let's look at the first. As introduced earlier, Rust for Linux involves integrating Rust with exciting Linux APIs. We analyze the wrapping status of various Linux subsystems APIs. Some subsystems like scheduler, memory, clock, and IRQ subsystems are well wrapped, while others like file and network subsystems lag behind. This is reasonable because scheduler, memory, clock, and IRQ subsystems are common in various drivers, while the others are used in the specific domains. The second is patch distribution. We categorize the patches submitted to the community into three types: safety abstraction, ROT compiler modification, and subsystem improvements. Initially, efforts focused on the key-build subsystem, but over time, the emphasis shifted towards enhancing safety abstractions. This implies ROT for Linux ecosystem is maturing currently, allowing developers to focus on writing new drivers and subsystems in ROT. The third is the development trend. There are more and more patches under review, but the accepted ones are not as so much. Meanwhile, the reviewing time for the accepted patches is also increasing. It seems that the review process for patches has become a bottleneck. After knowing about the general information of ROT for Linux, let's move on how to construct safety abstractions, which will be used to write drivers that we will explain later. This process involves data structures and functions. ROT Beijing can generate code matching said memory layout, allowing ROT to access said data structures and functions. The below blocks present an example. However, ROT cannot translate all C structures directly. For example, ROT lacks support of bit field and unions. Encapsulation involves securely translating data structures from C to ROT, ensuring safe and effective integrations. Then, if one data structure is correctly initialized, its reference is valid and secured by the ROT difference process. As for the functions, ROT summarize their use conditions and annotate them with 3 types of comments. The driver developers need to read these comments and call the function in the fixed orders. ROT pointers are also checked in the ROT for Linux. By ROT type system, function pointers are implemented as traits. Therefore, this avoids dereferences non-pointers. Writing new drivers in ROT allows a similar workflow with C, establishing the device, writing operation logic, and cleaning up resources. In this process, with ROT for Linux, the API interface provided are fixed. Unlike in C, which is more flexible, this poses competitive issues when previous C implication might have been simpler, but transaction to ROT requires more code to achieve the same functionality. Let me give another example. In Linux, there is a macro called container_of, which many Linux developers are familiar with. This macro is typically used with intrusive linked lists. As seen in the left diagram, there is a larger outside structure containing a smaller inner structure with a linked list. When we have the address of the inner structure, we can use container_of to find the address of the outer structure, because in C, the offset between a structure and its inner structure is fixed. However, implementing this in ROT becomes challenging. Why? Because ROT requires ownership to be handled strictly. The inner green structure needs to be wrapped in a pointer rather than directly nested inside many other structures. This wrapping of the pointer means that the offset between the inner and the outer side structure is no longer fixed, making container_of ineffective in this scenario. This example illustrates that when developing drivers in ROT, the most significant difference compared to C is that ROT imposes strict eliminations on programmers' capabilities. Therefore, certain programming techniques commonly used cannot be directly applied in ROT. After knowing about ROT's status, we started to evaluate its safety, performance, and development efficiency. according to the initial goals in the R4C patch. So our first step is to examine the current performance of ROT for Linux in terms of security. We have compiled data from various sources on the number of reported bugs. The most critical are the soundness bugs on the right, which relate to safety. This bit ROT abstraction aiming to be safe. They can still have bugs because these abstractions are human-made, not machine-generated. Therefore, human-made abstraction may inherently contain faults. Then we need to verify if all drivers can truly be implicated purely with safe interfaces without resorting to unsafe calls. Unfortunately, our analysis of various common ROT drivers shows that unsafe usage primarily stems from two main reasons. First, the inherent complexity of driver logic often necessitates the use of unsafe methods that cannot be entirely replaced with safe equivalents. Secondly, the safe abstraction layer itself cannot completely eliminate the need for unsafe methods. The idea was to wrap unsafe operations into an inner layer firstly. However, in practice, function interfaces expose unsafe aspects, and fixing these unsafe exposures can be time-consuming. A real-life example is that it took nearly 2 years to completely secure an interface called pin-init. Next, we process to examine whether ROT for Linux can truly achieve zero-code development of Linux drivers. We verify this by selecting several common drivers from the community, including those for files and networks. First, we accepted the overhead in terms of binary size. The figure on the right primarily compares the size of text, data, and BSS across various drivers. Drivers marked with asterisks indicate functionalities implicated in both ROT and C. The lower three drivers lack features implications. Among these, ROT consistently have larger binary size when implicating equivalent functionalities. This is partly because in common Linux drivers, debug segments are often omitted. However, for embedded devices where debugging remains important, the debug segment inclusion remains critical. Our analysis of debug segments revealed an interesting fact. Due to ROT, the language features, even without implicating equivalent functionalities, ROT binary size can experience significant bloat in the debug segment, occupying larger memory space. Furthermore, we delve into the runtime performance across different types. First, we evaluate the latency. For example, we tested both E1000 and Binder. Since the E1000 lacks features implications in ROT, the current performance overhead is substituted, with ROT showing significantly higher latency compared to C. For Binder, which now includes feature implication, ROT and C performance are quite comparable. Additionally, from the perspective of throughput, examining performance across different drivers reveals an overall trend. In similar terms, lighter colors indicate similar performance between ROT and C, while darker green indicates better ROT performance and deep red denotes better C performance. In most cases, ROT and C performance are similar, though there are extreme cases where C or ROT may perform notably better. We conduct investigations into reasons behind these performance trends. Firstly, Why Rust have poor performance? Due to Rust extensive use of smart pointers, it often breaks the principles of placing different structures into a tightly packed environment, leading to higher cache miss rates. Secondly, Rust runtime checks also contribute to performance overhead. Conversely, while Rust sometimes perform better, we found that Rust tends to excel in scenarios with less intensive memory use, where cache miss impacts are less pronounced. This advantage stems from Rust's use of smart pointers, which can lead to smaller structures compared to C. That's better utilizing cache lines. Using a taught example Rust structured cache lines, we confirmed that Rust structure generally occupy smaller cache lines compared to C. Another potential reason is that Rust's lack feature implications may result in smaller code paths, which can also contribute to better performance. Finally, our last evaluation item is the development efficiency. Does Rust offer advantages over C? Rust include built-in tools such as code coverage detection and CI testing systems, which contribute to higher code quality compared to other emergency Linux subsystems. Whether in terms of documentation code coverage or CI system test results, Rust have better experiences compared with other subsystems. Furthermore, when Linux introduced Rust, it attracts younger developers. Our observation confirms that Rust indeed has a higher preparation and quality of developers compared to other emergency subsystems. The third research question is learned lessons when we are researching and developing Rust for Linux drivers. If you use Rust for Linux, remember Rust development cannot solely rely on its compiler mechanisms to ensure safety. We also need tools like Rustbelt and Mengwei to further guarantee the safety of the code. In developing with Rust and C, we cannot use the same approach entirely. As mentioned with the container of example, when rewriting or writing new code, we must adopt Rust ownership principles. The use of unsafe code is unavoidable sometimes, so we need to accept the necessity of use unsafe code when required. If you are developing new drivers, it's advisable to start with subsystems that are more prone to bugs, focusing first on those with poor code qualities. At last, I want to summarize the key takeaways. Rust can ensure memory safety, but it comes at the cost of programming flexibility. Not all C drivers can easily translate into Rust. There is no silver bullet for security. Rust does not provide an absolute guarantee of safety. It is an improvement, but it is not a complete solution. While Rust claims zero-code abstractions, we found it to be more realistic, described as nearly zero code. It does not provide an absolute guarantee. Finally, I want to thank my team and my co-authors. This paper is inspired by our project ROS, which is a Rust-based dual kernel system that has been successfully tested on a satellite. Our work is open sourced on GitHub, and you are welcome to explore it further using the QR code provided. Thanks for your listening, and you can reach us from the above emails. Please feel free to contact us.